Hello everyone, thank you for joining today's webinar on why shifting to zero prototyping in the design of high voltage submarine power cables. I am Sumit Singh, an electric motor expert at EMWorks. EMWorks is a leading provider of electromagnetic simulation software for electrical and electronic design from DC to millimeter wave frequencies. Our products are embedded in the most popular CAD platforms, namely SolidWorks and Inventor. They cover a wide range of applications ranging from electric motors, generators, transformers, and power electronics at the low frequency end of the spectrum to antennas and various wireless circuits and components at the high frequency end of the electromagnetic spectrum. Moving ahead, now let us look at the agenda for the technical presentation. First, I'll be talking about high voltage power cables. Next, we're going to look at some of the design challenges that engineers face in designing these high voltage submarine power cables. Next, we will go over some results of simulation for configuration of high voltage cable. Then, I will also get an opportunity to show you our EMS products. Finally, we will conclude with what we have seen. Let us look at high voltage submarine power cable. What are they? As the name suggests, these are cables that are buried underwater, basically oceans or sea. So they are also called submarine power cables. It works by getting energy from a source out over water, usually by wind turbines, and using massive cables that lie on or under the seabed to transfer that energy to the land. They typically carry 3 phases, but they are not restricted to carry 3-phase electricity. They need to have high flexibility and strength because they are buried deep under the water. Let us look at some of the advantages that they present. Now, they have excellent insulation. What I mean by insulation is electrical insulation. The solid XLPE, which is really the core of the submarine cable, presents this factor. They don't need any oil to achieve their cooling. They have a wide range of operating conditions, all the way from 1 kV to 500 kV. Because of the structure that we look at little more intimately, they have very good mechanical performance. It covers great distance and water depths and are designed to operate in dynamic submarine environments for many years. Now, naturally, then the application for these cables are in areas where there are some offshore activities going on. For example, oil and gas drilling, marine platforms. These cables often act as conduits to supply power to these offshore installations, and after this tsunami there have been a lot of subsea observatories installed by various governments in various parts of the oceans, and so this tsunami pre-warning systems also require electricity, and these subsequent cables often carry the electricity from a nearby island. Now, before looking at the design challenges, let us look at the structure of a subsea power cable. For example, here on the right I have a cross section of one such commonly used design for these cables. You can see that these conductors are there. You can see in the brown color. They are the ones that carry electricity. Then these conductors are covered with lead sheet. As you can see on the screen here, these lead sheets are basically there to block the electric field from leaving the sheet. Then we also have twisted outer armor, which is here on the outer body, which provides mechanical strength, and all of these are packaged inside XLPE, which act as an insulator, which act as an excellent electrical insulator. So these are filled here. Now, As engineers of these cables, what are some of the performance characteristics that we are looking at? First, they would like to get an idea about the capacitance and the resistance that these cables offer. Then, they would like to know if the voltage carrying capacity of these cables are indeed there for the ratings that have been designed for. So what I mean by that, it is the electricity field. So what I mean by that is the electric field distribution inside the cable becomes important, and they would also need to study breakdown of these cables should any fault occur. Finally, losses play a very important role. These lead sheets have eddy current losses, and it's important to calculate them. Also, the armor, which is typically made of steel, have losses in them, and it's important to calculate them. And finally, the temperature distribution inside the cable becomes important because we need to make sure that thermally the cable does not get too hot. So once that the simulation we ran, let us look at the comparison of inductance, resistance and inductance. To begin with, we performed a capacitive analysis for a 3-phase power cable, and we calculated its analytical phase capacitance, which is around 0.166 microfarad per kilometer. We also referred the IC standard, and as you can see, for the software EMWorks 2D, we got around 0.166 microfarad per kilometer. Notice that the capacitance calculation coming from the simulation of a cable designs confirm very well with the IC standard. Moving ahead, similarly we performed an inductance analysis for 3-phase power cable. Analytically we got 0.4 millihenry per kilometer, and using our software EMWorks 2D we obtained 0.48 millihenry per kilometer, and also using the another tool, that is EMS 3D, we achieved 0.43 millihenry per kilometer. Similarly, as per the IC standard, our results are closely matched, and which is nothing but around 0.41 millihenry per kilometer. Same goes for the resistance calculation. We performed DC resistance analysis of the 3-phase power cable analytically and based on the IC standard, and using our both EMWorks 2D and EMS tool. The degree of error is less and in this computation, so we can conclude with a lot of confidence that simulation can be adopted for finding out the capacitance, inductance and the resistance of these cable designs. And as a result, when you have a new design of the cable done using a computer, we can use finite element analysis to compute its performance, namely its capacitance, inductance and resistance. Moving ahead, let us look at the simulation results when it comes to electric field and breakdown voltage. Now you have noticed here that all these metallic sheets are grounded, and then the conductors are kept at their respective electric potential. Now there is going to be an electric field in the dielectric or in the insulator XLPE, and that electric field must be within the breakdown voltage of all operating values of the voltage. Now EMS electrical simulation helps you to understand the electric field distribution and the breakdown voltage. In the design of this cable, the lead sheets are properly grounded, and as a result, the electric field is confined inside the lead sheet. The lead sheets actually act as a Faraday cage, as you can see here on the image, and the XLPE is chosen in such a way that its breakdown voltage is much higher than the electric field that is achieved inside the lead sheet. Electrical breakdown or dielectric breakdown is a process that occurs when an electrical insulating material, when subjected to a high enough voltage, suddenly become an electrical conductor and electric current flows through it. And insulating materials undergo breakdown when the electric field caused by an applied voltage exceeds the material's dielectric strength. The voltage at which a given insulating object becomes conductive is called its breakdown voltage, and it depends on its size and shape. Cables are likely to fail in operation due to disruptive breakdown. If the dielectric used is defective, a puncture may occur and the cable may fail. Normally, such defects are detected in the laboratory tests and eliminated at the time of manufacturing. Failure of cables due to breakdown, puncture, or of dielectric is usually very rare. Here you can see the electric field distribution in a cable, and also we can compute the electric safety factor using the EMWorks tool. Next, we will focus our attention to a section of this cable. We will particularly look at loss analysis, where all those losses happens in the high power cable. Obviously, the conductors that carry the current, there is an I2R or copper losses. There is also eddy current losses in the lead sheet because the current that is being carried is alternating current. There will be a losses in the armor based on the material of the armor. If the material is copper, then there is going to be a very little eddy current losses, versus if the material was steel, then there is going to be a core loss occurring in the steel. Finally, there is also going to be a dielectric loss in the dielectric medium, which we will ignore in this session. All these losses will lead to a rise in temperature in the coil, and the idea is really to understand the temperature distribution in the coil. So next, let us look at the effect of armor material on the total losses. As I mentioned earlier, we have a choice of the material which is used to create the armor. For this example, we have used a magnetic flux density of the armor permeability as 1 and as 300. We can use copper or aluminum, they are excellent conductors. Or we can use steel, which is not a very good conductor, but it has some permeability. And let us inspect what losses we get. When I use copper or aluminum, I get very little losses in terms of the armor loss, versus if about to use the steel. I have losses that is almost 17 or 18 times more than that per unit length. So the conclusion here is that the steel armor results in higher losses, but it is still preferred. And it is preferred because of the mechanical properties and mechanical strength that steel offers. So as you can see, with permeability of 1, we got the armor total loss as 1300 watt per kilometer, and with the higher permeability, we get the total loss around 1440 watts per kilometer. So obviously there is going to be some sort of trade-off between mechanical strength and the armor losses. Next, let us see what the fundamental reason is why we are providing this twisting of the armor. Notice the two figures here. The one on the left hand is an untwisted armor. You can see in the blue color it's straight, and then in the right we have twisted armors, where as you can see here it's twisted. In the previous slide we established that we would use steel as the material for armor wires, and the reason despite having higher losses is because it provides better mechanical strength. So let us see the result of the simulation. Now we did simulation to understand what kind of losses happen when you have untwisted steel versus twisted steel armor. Certainly, twisted steel armor results in a much lower armor losses, and that is really the reason why we use twisted armor wires to fabricate these cables. And you can see here the total loss was decreased from 1.4 kilowatt per kilometer to 1.22 kilowatt per kilometer. Moving ahead, finally let's look at the temperature distribution. EMS can be coupled with a thermal conduction solver. Together, the magnetic and thermal conduction solver can compute the temperature distribution in the cable, as you can see here. And for this cable, the maximum temperature is limited to 33.45 degrees Celsius, which certainly is within the design specification of the cable. And you can have a distribution both in 2D and as well as in the 3D model. Next, I'll be showing you a 3D simulation of the XLPE twisted cable and some of the objectives that we are interested in computing the armor loss. We are also interested in computing the eddy losses in the sheet. Finally, we would like to understand the magnetic field distribution and observe the skin and proximity effects in the copper and the lead sheets, as you can see here. So now I'll be using EMS 3D for a quick demonstration of the mentioned points in the previous slide. Now I have a twisted cable 3D model inside SolidWorks. You can see the outer region represents the seabed, and then there is this cable. Contrary to the 2D similar that we saw, we have a definite length of the cable. So we are going to do using EMS for SolidWorks a 3D simulation on this cable. EMS for SolidWorks, just like EMWorks 2D, is an add-in product, and the simulation can be accessed right inside SolidWorks. The first step is to create a study. Here we have created this, what is called a AC magnetic simulation. In the AC magnetic simulation, it is mandatory to specify the frequency with which the current is carried by the copper conductors. Also, the AC magnetic simulation can be coupled with a thermal conduction solver to give you the temperature distribution, as we did in the 2D simulation. We must specify materials for the various components. The three inner conductors, they are made up of copper. Then the outer layer or cellular are made up of cellular polyethylene, is where the twisted armor are situated. The dielectric is made up of XLPE, and here is the twisted armor material made up of steel, and the sheet is made up of lead. Once the materials are defined, we can use the definition of coil to tell the program how the current is carried by these conductors, and they are done with the help of what is called as a solid coil. Here the conductor carries a current, and you can see the current enters on the left, and then current leaves the model on the right side as denoted by the arrows. Once you define the current, then you need to go ahead and then specify the RMS value of the current, and then also specify the phase angle. Now, because we have three conductors carrying current at three different phases, you can now specify the phase shift between the two conductors. So it will be 0, 120 degree and 240 degree for the three phase conductors. So similarly, I have defined coils for the second and third conductors. Now let us look at some of the results, and prior to this webinar I have run the simulation, so we can jump straight into the results. Now a lot of these results are packaged into the results table. For example, you can calculate the inductance, the self and the mutual inductance for all the conductors. Also, the impedance is calculated. Finally, one can look at all the losses. For example, these are the solid losses, I square R copper losses occurring in the conductor. Similarly, you can see the losses in the lead sheet which can be added, and all the losses that occurs in the twisted armor is also produced in this table. EMS is a 3D finite element software, and hence it has some powerful visualization in 3D. For example, users can visualize the magnetic flux density. Here is a plot of the magnetic flux density in and around the cable. Notice that the steel armor provides excellent shield to the magnetic flux density, and as a result, you can be assured that the flux density does not escape the cable. Next, we can look at the current density. Here I have the 3 cables and the lead sheet, and you notice the current passing through these cables, and you can also see both the skin effect as well as the proximity effect in the distribution of current. Last but not the least, the losses are important. EMS helps you to visualize the losses. In this result table, we saw the value of these losses. In the plot, we can see the location where these losses are likely to occur. If we zoom in, you can see very high losses which are in perfect correlation with the current distribution. You can now see the losses through all the potential components, the conductors, the lead sheet, and the twisted armor. Notice that the blue is low value of these losses. Now I can isolate them. For example, I can just look to observe the losses in the twisted armor and the losses in this lead sheet specifically. So we just saw how EMS can help you to simulate these cables and find a lot of interesting and valid information that is required for an engineer who designed these cables. Now, to conclude this technical presentation with what we saw how EMWorks product, namely EMWorks 2D and EMS 3D, can be used to study the performance of the cable. We saw how we were able to calculate the capacitance, inductance and resistance of the cable. Then we studied the electric field distribution inside the cable and also studied if there was indeed any breakdown. And for the design that we investigated, we found that for the operating conditions there was no breakdown. Next, we went to EMS 3D and we studied a particular length of the cable as a 3D model. This allowed us to calculate things like magnetic flux distribution in and around the cable. We were able to visualize and quantify the losses occurring within the cable per unit length. And we could do a thermal simulation to look at the temperature distribution. All these simulations were carried out right inside SolidWorks, and there was no export or import of 3D geometry, and as a result, users of EMS have a very short learning curve to do magnetic and electric simulation. Thank you for attending the webinar. Now the session is open for a Q&A, and see you in the next webinar. Thank you.